Hello, welcome to Basics of Noise and its Measurement. I am Nachiketa Tiwari. Today is the fifth day of fifth week of this course. This week we have been discussing Fourier series, Fourier integral, and today we will be discussing Fourier transform of various functions which may not necessarily be periodic in nature. The technique of Fourier transform is extremely powerful, and it is very widely used across all sorts of domains when we want to represent a time signal in frequency domain. This technique helps us in several ways, and most importantly it helps us resolve or identify specific frequency components of a signal which contribute to the generation of a signal in time domain. So suppose we have a complicated time signal, that is a signal which is a function of time, and if we are interested in finding out what are its frequency components which are dominant, then, and if the signal is not necessarily periodic in nature, then the method of Fourier transform, this technique, it helps us solve this problem. And in that sense it's extremely powerful and very widely used. Specifically in area of noise, it's used almost everywhere, and that is why it's important to understand it. Now the other thing I wanted to mention was that what we will be discussing today is Fourier transform from a theoretical standpoint. But when we use computers to conduct these transforms, to develop these transforms, then we use a slightly different method. So we don't use analog formulations of the method, and what we do is something known as DFT, that is digital Fourier transforms. So that is something we will cover in the next class, or actually next week, but today and tomorrow we will cover more or less pretty much the details of Fourier transform from a mathematical and an analog standpoint. So you would wonder that you have these Fourier integrals which we have already discussed, and they help us represent a signal in frequency domain even if these signals are not periodic in nature. Then what is the additional advantage we get from Fourier transforms? So the answer to that is that Fourier integrals, which we discussed in the last class, they are essentially valid for real functions, But if our function is complex in nature, because in acoustics and in noise, a lot of times we handle complex entities. For instance, we had discussed complex amplitudes, complex frequencies, complex time signals. So then if we have to resolve these type of signals in the frequency domain, then that is where Fourier transform comes in handy. So that is the backdrop. So let's consider a function ft, and we have seen that its Fourier integral is 0 to infinity a function of omega cosine omega t plus another function b of omega sine of omega t d omega. So this is the Fourier integral. Okay, and we had seen that a of omega equals 1 over pi 0 to infinity, excuse me, it's minus infinity to positive infinity fv cosine of omega v times dv, and b of omega is 1 over pi minus infinity to infinity f v sine of omega v dv. So let's number these equations. This is equation 1, this is equation 2, this is equation 3. So if I do my mathematics, and what I do is I put this here and this equation in place of bw, b omega, then my f of t equals 1 over pi 0 to infinity, and instead of a omega I am going to put this entire expression. So this is f of v cosine of omega v, and I have to integrate it from 0 to infinity, and then cosine of omega v times cosine of omega t, plus instead of b omega I am going to put this expression. So it is f of v sine of omega v sine of omega t, and I have to first integrate this whole expression with respect to dv, and then I have to integrate this thing with respect to d omega. And the other thing which is erroneous here is that this limit should have been minus infinity to infinity. Okay. So this is equal to 1 over pi 0 to infinity minus infinity to infinity. I'll take f v as common, and in the parenthesis I'll have cosine omega v times cosine omega t plus sine omega v times sine omega t, and then I have dv and d omega. Now I know that cosine of a minus b equals cosine of a times cosine of b plus sine of a times sine of b. So this is of that form. This entire underlined term is of this form, which is cosine of a minus b. So what I do is I rewrite this expression f of t equals 1 over pi integrated from 0 to infinity minus infinity to infinity f of v, and then cosine of omega t minus omega v, and this has to be integrated first with respect to dv and then with respect to d omega. Now we look at this expression and we make some observations. So the first thing we note, so let's call this whole thing, this whole integral of fv cosine omega t minus omega v times dv, when I integrate it, let me call this as capital F of omega. So it is not just the integrand, it is the integral of the entire expression. So we make some observations. The first thing is that cosine of omega t minus omega v is an even function. With respect to omega. Second, when I integrate this whole thing, f of v times cosine omega t minus omega v dv, then the integrand of f omega has v, but once I integrate it, so once I integrate it, f of omega is independent of v. It is independent of v, and from these two I can say that the integral of this fv cosine omega t minus omega v, that is minus infinity to dv, this thing, the integral, that is this thing, is nothing but 0 to infinity 2 times the same thing. I can make this deduction from this. So what I can do is I can rewrite my ft as 1 over pi 0 to infinity 0 to infinity again, and then instead of, so now because I have changed the limits, so I am going to put 2, so excuse me, it's 2 over pi f of v cosine omega t minus omega v dv d omega. Okay. So this is one part, and this I can write it as 2 over pi 0 to infinity, and I can write this integral as f of omega t omega. So what I have done in this class till so far is that we started from a function, right, from a Fourier integral. We substituted the values of a omega and b omega into the Fourier integral. I mean, that's all we have done. We have substituted those values, did some mathematical manipulation, and we have transformed this equation f of t as a function which is nothing but 2 over pi integral of f of omega d omega from 0 to infinity, and where f of omega is defined as this function, which is f of v times cosine omega t minus omega v times dv integral of 0 to infinity. So this is what I wanted to cover in this lecture, and I will continue this in the next lecture also, because what we have done till so far, it has to continue, and then finally we will arrive at the Fourier transform of the overall system. So please be tuned, please stay tuned, and we will continue this discussion and close this in the next lecture. Thank you.